meeting together on February 20, 2023, in the headquarters of the BBVA Foundation in Madrid, Spain, in order to deliberate and decide, the jury has resolved to grant the BBVA Foundation Frontiers of Knowledge Award in the Basic Sciences in its 15th edition to Paul Corkum, University of Ottawa, Ferenc Krauss, Max Planck Institute of Quantum Optics, and Anne Louillet, Lund University, for pioneering studies of ultra-fast processes and breakthroughs in attosecond science. They have shown how to observe and control the motion of electrons in atoms, molecules, and solids with ultra-short light pulses on timescales of 100 attoseconds. 1 attosecond is approximately the time for light to travel across an atom, and it is the natural scale for electronic motion in matter. This time scale was previously inaccessible to experimental studies due to the lack of light pulses of sufficiently short duration. Anne Louillet performed path-breaking experiments to produce light with very short wavelengths and duration that were seminal to attosecond probing of matter. Paul Corkum developed experiments and an intuitive physical picture for short wavelength light generation, which ultimately allowed the imaging of molecular orbitals. Ferenc Krauss generated ultra-short single light pulses and used them to probe electron motion in atoms. These groundbreaking contributions have opened exciting new frontiers in different areas, including atomic physics, photochemistry, and material science.
Could you define the field of attosecond physics and why it's so scientifically valuable to observe the motion of electrons at this timescale?
So let me begin by saying what an attosecond is. It's incredibly short. So an attosecond is to a second as a second is to the age of the universe. Can you imagine something so short as that? I could say it differently. An attosecond is a billionth of a second, and you take one of those billionth of a second and a billion again, and that's an attosecond. A billionth of a second is 1 attosecond. Now, electrons move on the time scale of attoseconds. You sort of know that because they go such short distances in, say, atoms and molecules, and they're very light, so they move very fast, and the forces on electrons are really strong. And so they change their environment in a few tens of attoseconds. And so if you want to look at electrons and you want to see what happens to them, then you need attosecond science. For example, you might try to do something to an atom, and how fast do all the electrons respond to that? How fast can they get in? And that's the fastest time scale that electrons are able to have in materials.
Could you explain your specific scientific contribution to this field of research and its importance for its development?
I think it's for the model of how you make attosecond pulses, and it's incredibly simple, so I can explain it to you, an audience that probably doesn't know about attosecond science to start with. So I do it by an analogy. I grew up by the ocean in New Brunswick. And so you may not have grown up by the ocean, but probably everybody's been to the ocean, and you see seaweed on a rock. And you can watch a wave come in, and it picks up the seaweed, and it moves it up, and it brings it back down again, and it crashes into the rock from which it left. So that's the analogy of how attosecond pulses work. Imagine an atom, that's the rock. Along comes a light wave, that's the wave, it's a wave of force on an electron, just like a water wave is a wave of force on a seaweed. It pulls the electron away from the atom, but then it drives it back again, and it crashes into the atom from which it left. And in that crash, you create an attosecond pulse, or maybe a few tens of attoseconds. And that's how it's done. It's that simple.
And what potential applications do you foresee that attosecond physics could bring in the future?
It's hard to see the future, so you don't really know, really. I think one thing to think about is we've learned to make attosecond pulses in atoms. We've learned to do it in molecules quite quickly after atoms. More recently, we've learned that attosecond pulses can be created in solids. Solids like a piece of glass, solids like a semiconductor or something like that. And so we've now brought attosecond pulses together with modern solid-state physics, and modern solid-state physics knows how to structure the surface of materials with exquisite precision. It's amazing what they can do. And so we can bring these attosecond pulses and this exquisite control over surfaces of materials and learn to focus the attosecond pulses to very, very small sizes. As a matter of fact, these will be very, well, maybe there are other ways to do it, but this will be an easy way to do it. Now, that's important for solids, it's important for maybe electronics, it's important for things like that, but it's also important for biology. Imagine yourself, you're made of cells. Inside the cells, what makes the cells interesting is that there are all kinds of little compartments called organelles, and the size of these organelles is very small, on the order of about 50 or 60 nanometers in size. And so if we can make foci of material that are 50 and 60 nanometers, all in short pulses, and we can take material out of the cell and put it in the vacuum and measure it with conventional means, then we have a way of looking at cells in a way that we've never been able to before. And so possibly the implications were strong for biology.
Could you explain your contribution to the field of attosecond physics and how it contributed to observing the motion of electrons in atoms?
We have pushed the frontiers of ultrafast laser science to its ultimate limit by generating pulses of laser light that consists of a single wave cycle of the electromagnetic field. For this generation, we have used a technique that has been pioneered by the co-winner of this prize, Anne Louillet. And we have used another technique that has been proposed by the other co-winner of the prize, Paul Corkum, for measuring the duration of these pulses. So the establishment of attosecond physics is a multilateral, multinational effort. With these tools and techniques, scientists all over the world have been able to look into processes that evolve within atoms, molecules, and also solid matter with the participation of electrons, and have been able to observe the motion of these tiny, extremely fast particles in real time.
Following your groundbreaking contribution 2 decades ago, what in your views have been the most important discoveries achieved in this field?
Attosecond technology has enabled us for the first time to observe directly the motion of electrons in molecules, which happen to be the functional building blocks of all living organisms. By tracing and gaining insight, very deep insight into these processes at the most fundamental level, at the level of molecular interactions, we have the chance to understand much better the processes underlying life and underlying all processes that are relevant for life. On the technical side, electrons play another extremely important role. In nanocircuits, they are responsible for switching on and off electric current and in this way processing information at ever higher speed. If we wish to expedite this signal processing to build ever more powerful computers, again, we need to understand the way electrons move in these tiny dimensions. And by doing so, we have the chance to advance electronic signal processing to its ultimate limit to the oscillation frequency of visible light.
Could you explain the potential medical applications of attosecond physics which you are working on and how they could be used to prevent diseases?
The first decade of attosecond science has been about looking into fundamental processes, fundamental electronic processes in atoms, molecules and solids. After doing so, we have realized that the ability of actually measuring not just electronic motion, but also the oscillation of the electric fields of light opens the door for perhaps the first real-world application of attosecond science. By hitting molecules with extremely short infrared laser pulses and probing, sampling the electric field, the excited molecules send out in the wake of this ultra-fast excitation, we have been able to measure with never before achieved sensitivity molecular signals that contain information about the atomic structure and atomic composition of the molecules under scrutiny. We have been using this technique for scrutinizing tiny, minuscule changes of the molecular composition of human blood and use this ability to distinguish blood samples of cancer patients from blood samples of healthy individuals, and recognized that we can indeed detect reproducible changes in this infrared electric field molecular signal, and we have been able to use this for distinguishing persons who carried a tumor in their body from those who happen to be healthy. In this way, we may be able to actually detect all kinds of cancer, but most probably also a number of other diseases, opening the door for a broadband health monitoring by using infrared molecular fingerprinting.
Could you explain the original experiments you carried out in attosecond physics and why they were, in words of the jury, path-breaking for the development of this field?
These experiments consist in detecting high-order harmonics of the laser field. So when you expose a gas of atom to an intense laser field, it's possible to generate very high-order harmonics of light. It's very similar to when you play violin and you hit the strings of the violin with a bow, then you generate not only a tone but overtones. It's the same thing but in light. So these high-order harmonics can go from the infrared, where you start from, to the extreme ultraviolet range of the spectrum. And it was conjectured already at the beginning that possibly these high-order harmonics would lead in the time domain to very short light pulses.
What have been the most important advances in attosecond physics since you first carried out your pioneering experiments?
There has been several steps. First, after these first experiments in 1993, the understanding of the physics behind this phenomenon. and at the same time also the realization that indeed in the time domain we could have very, very short light pulses in the attosecond range. Then, very important, 2001, the demonstration that we had attosecond pulses, both in a series and also single attosecond pulse. A few years later, 2010 maybe, the first experiment where one could really detect electron motion using these attosecond light pulses, and also at the same time the opening towards application in physical chemistry and condensed matter.
Looking into the future, what do you think are the most promising lines of research in this field and its possible technological applications?
It's very difficult to predict the future of this field. At the moment, this field is really exploding into many directions. There is, of course, atomic physics and getting closer to quantum information, which I find very exciting. You have molecular chemistry, looking at charge motion at the beginning of a chemical reaction. Condensed matter, looking at charge dynamics, spin dynamics in materials. There are also applications in industry, and the semiconductor industry is interested by this broadband radiation. And there many things happen. You have also progress in laser technology that leads to progress in these sources.